Okay, so now we're going to talk about tangent vectors and integrals within three-dimensional space. Okay? So if we have R of t, which is a parametric equation describing a curve in space, well, how do we do its derivative in integrals? Well, I mean, if we want to do its derivative, we take the derivative of each individual piece of the problem. Okay. Now, if we want to do its integral, yeah, the integral is just the integral of each individual portion of the problem. And this follows the same type of logic that what we learned in Calculus 1 is extended into higher dimensions, and it follows the same rule. As a matter of fact, the dot product and the cross product, they follow the product rule. I mean, so if you do the derivative of u cross v, that's u prime cross v plus u cross v prime. Same thing with the dot product. If you do the dot product in three-dimensional space, it's a derivative of u dot v is u prime dot v plus u dot v prime. Okay, so it follows the same logic as our basic understanding of calculus. We're just going to take the integral or the derivative of each individual component. Okay, so let's just, I'm just going to separate this into two videos, but I actually think this would be better for me to do this as one video. We're going to do, this actually bridges across two sections of y'all's book. This will extend between 13.2 and 13.4. So let's first just take a derivative, and then we're going to do another problem where we're going to do an integral, and we're going to go from acceleration up to velocity and go up to position, and we'll find the position of a particle in space. And this becomes very important when some of y'all are physics type of people. Why is this stuff so important? This stuff got us to the moon. It's going to get us to Mars. So that's why it's really important. Okay? So let's start off relatively simple in the sense that, let's say, R of t is going to equal t squared I plus cosine of t squared j, and then plus sine squared of t k. Okay. So let's try to think about what L prime of t would be. Well, the derivative of t squared is 2t. The derivative of cosine is negative sine of t squared, but we have the same rules from calculus that we have to obey the chain rule, and so that becomes 2t times j. And the derivative of sine squared, okay, we're going to have to do the chain rule on this guy, so we're taking the derivative of the square first. So that would be 2 sine of t cosine of t okay. That's it. So it's the same rules that we had learned from calculus. Okay. Now let's try to figure out how to find the equation of a tangent line. So remember, whenever we're calculating slope, you're calculating the slope. This will calculate the slope for any point. But what if we wanted to actually find an equation of a tangent line within three-dimensional space? So let's say, let's find the equation of the tangent line of say x, which equals t, y, which will equal e to the minus t, z, which is going to equal 2t minus t squared. And we're going to try to find the equation of this tangent line at a point. So we're going to try to find it at 0, 1, 0. Okay. So, remember when we were talking about parametric equations of lines in space, we need a point in space. That's our point right there. Okay, so we're going to try to find the equation of the tangent line at that point. But what else do we need to describe a line in space? We need a vector that is parallel in the direction of the line and a point to fix that vector on there, and then we can find the parametric equation. All right? So we already have a point. That's fine. But now what we need to do is we need to find the derivative of this, which will give us a vector that will be tangent to this curve in space at that point. Okay? But to find a vector that is going to be parallel to the derivative at this point, the first question you need to ask yourself is what t-value is represented by this point in space. So we have a parametric equation describing a point in space. Well, for what t-value would we actually be at the point 0, 1, 0? This one's not too bad because you just put 0 into this guy right here, we get, well, t which equals 0. So at t which equals 0, we will be at the point 0, 1, 0. So I'll put 0 to this, it's 0, 0 to this, it's 1, 0 to that guy, it's 0. Okay? So the point does have to exist on the curve. You can't find a tangent line to occur to this point on a point that doesn't exist on the curve. Okay? So yeah, t which equals 0. And so now what I'm going to do is I'm going to say, okay, what is r prime of t at t which equals 0? That will provide the vector that will be tangent, vector that will be parallel to the tangent line at that point. Okay? So, r prime of t will equal, okay, derivative of t is just 1, and then this would be negative e to the minus t. And this would be, okay, so that would be derivative of 2t is 2, derivative, that is minus 2t. Okay? So, r prime at 0 will equal, well, 1 is 1, even 0 is 1, but it's negative, so that's going to be a negative 1. But if I plug 0 into this guy right here, what do I get? I get 2 minus 0. So that would be 2. Okay, so what do we have at this point of our problem? We have a point in space, 0, 1, 0, and we know that at that point, the tangent line will be parallel to this vector right here. So this gives us a way to parameterize this problem. All right? So the parametric equation for the tangent line at this point well, I'm going to fit it on this page. X is going to equal, all right, so that's the x value right there. 0 plus 1 times t, so that's just going to equal t. Okay. Y, my y value is right there, 1, and then I have a negative 1 right here, that's minus t. Well, that's just 1 minus t. Okay. And then z, okay, I have a point right here that is minus 0. All right, and then I have this portion that is corresponding to the vector. which is going to be plus 2t. That's going to equal 2t. Okay, so if I wanted to write this in a kind of simplified format, I'll write it like this. So we're going to put this on this page. So the tangent line would be equal to t, comma 1 minus t, comma 2t. So that would be the parametric equation of that tangent line. And you might ask, well, all right, so we have an equation of the tangent line, but t is going to go on forever, backwards and forwards. Could we find an equation of a unit tangent line? We'll get into that in the next video. All right. The next video we'll consider, well, okay, you can find a tangent line, but does the tangent lines really describe everything about a curve in space? No. We have tangent lines, normal lines, binormal lines, curvature, and torque. We're talking about three-dimensional things. Okay? But instead of well, that'll be the next video. So let's actually, so this week is more about derivatives and integrals. So let's ask, if we were given an acceleration of a particle in space, how would we figure out the velocity of that particle in space and the position of that particle in space? Okay? And then we'll get into arc length and all the other stuff. I'm not exactly following y'all's book, but just follow along. Okay. So, we're talking about integrals and derivatives at this point. All right. So let's say we're given an acceleration A of t is going to equal 2t times I plus sine of t times j, and then plus cosine of t times k. But remember, whenever we're doing a problem involving acceleration and we're transforming it into velocity and position, we need an initial velocity and an initial position to actually fully create this problem. So, and say, all right, v of 0 equals I, and r of 0 is going to equal j. These are vectors. Okay. Find v of t and r of t. Okay. So we're given an initial acceleration in vector form, and then we're given our initial velocity and our initial position. R of 0 is going to be our initial position. I don't know why we switched from these to R, but let's do that. So I guess it's to distinguish between the vector form and scalar form. So given this thing right here, we're going to try to find the velocity and the position as a function of time. Okay. All right, and this is related to the fundamental theorem of calculus. And remember, when you're doing integration and you're using the fundamental theorem of calculus, I realize it might have been a little while for y'all, you need to make a change in variables. If you're going to integrate something and have its boundaries being in terms of t, you need to make a change in variables. So I'm going to change these variables into x's, but it's a dummy variable. Okay? It just means I'm integrating this guy with respect to x, but my boundaries are going to be in terms of 0 and 2. Okay? So, through the fundamental theorem of calculus, we're going to know that v of t minus v of 0 is going to equal the integral from 0 to t. And so that's why we're making a change of variables, is because this is v of t, this is v of 0. Our boundaries are going to be in terms of t and 0. And so that's going to be, and so I'm looking at this guy right here. I'm going to change that t to an x. That's going to be 2x with respect to x of I plus the integral from 0 to t minus is going to be sine of x with respect to x times j plus the integral from 0. Oh, sorry. I left one portion of the problem out. There's supposed to be 2 right there. Cosine of 2t. Okay. So that'd be the integral from 0 to t of cosine of 2x with respect to x times k. This is a problem I have to messing up. Okay, so what is this going to give us? This is going to give us the v of t. Okay, so now if I integrate 2x, well, if I integrate just x, that becomes x squared divided by 2. So that would just be x squared evaluated at 0 and t times I. And remember, when you integrate sine of x, this is backwards from the derivatives, and when you integrate sine of x, it inserts an extra minus sign into the problem. So that becomes negative cosine of x. So we have negative, now cosine of x, evaluated at 0 and at t, that's going to multiply by j. Okay. Now when I integrate cosine of 2x, that's not going to change signs. But since I'm integrating cosine of 2x to compensate for the chain rule, I'm going to have to divide by 2. Okay? So that becomes plus, now sine of 2x divided by 2. We've got to be very careful with the notation on this one, k. And what I'm going to do is I'm going to take this v of 0 that I have right here, and I'm going to move it to the opposite side. So whenever you think about this as, oh, I'm adding plus c to the problem, well, there's actually going to be quite a bit that gets inserted. So for this guy right here, t squared is 0. If I plug these 2 points in, I'm just going to get t squared. When I plug these 2 points into this guy, it's going to be negative cosine of t, but you have to remember, cosine of 0 is 1. I'm going to get a constant from that interval right there. Okay? When I integrate this guy right here, this is not going to present a problem. Because sine of 2t divided by 2 is just sine of 2t divided by 2. Sine of 0 is 0. But I have an extra vector that is coming from the fundamental theorem of calculus, which is my initial condition of v of 0, which is, it's up there, I. Okay. So, what is this going to give me? This is going to give me that v of t is going to equal, okay, so this just becomes t squared times I. Right? Now plus, this is going to be negative cosine of t plus 1 multiplied by j, and then plus sine of 2t divided by 2 multiplied by k, and then plus I. This v of 0 was I. So since v of 0 was I can combine it with the first one. So that becomes t squared plus 1 times I, now plus negative cosine of t plus 1 times j plus sine of 2t divided by 2 times k. Okay, so this is the three-dimensional representation of the velocity as a function of time given the initial velocity of the problem. Okay. So now that we have the velocity as a function of time, we're going to figure out r of t, which is going to be the position as a function of time. Just a second, I might have written that down a little too fast. This video will be posted hopefully tonight. Okay. So if you need to slow it down and review it, you'll have some extra time to do that. Okay. So we have found v of t. Now that we've found velocity as a function of time, we're going to try to figure out the position of this object as a function of time. All right? So we're going to look for r of t. We're going to do the same thing where I'm going to do a change of variables and make all of the t's that are in this one x's. Okay, so to the fundamental theorem of calculus, once again, we're going to say, r of t minus r of 0 is going to equal the integral from 0 to t. Okay? And so I'm going to take my first one, t squared plus 1. That's going to be x squared plus 1 having an integral with respect to x times I plus the integral from 0 to t. Okay. Goes to the next one I'm looking at. That's going to be negative cosine of t plus 1. So we change that into negative cosine of x plus 1, an integral with respect to x times j. Okay. And then we're going to go to our last one. Looking at velocity as a function of time. So we did this integral, and now we're going to do this integral right here. Sine of 2t divided by 2. So plus the integral from 0 to t of sine of 2x divided by 2 is the integral with respect to x, and then multiplied by k. This problem's a bit longer, so I'm going to do it at multi-levels like this. So what is this going to give me? This is going to give me that r of t. Okay. So this first one has become now x cubed. Well, x cubed divided by 3 plus x evaluated at 0 and at t, and multiplied by I, and then plus. Okay, so if I integrate negative cosine of x, this is going to be negative now sine of x. And then the integral of 1 is just going to be x. Now both of these guys are going to have to be evaluated at 0 and at t. And that's going to be multiplied by j. And then I'm going to have to integrate the sine of 2x divided by 2. So when once again, when I integrate sine, it's going to have to change signs. So this would be negative cosine of 2x divided by 4 and evaluated at 0 and at t, and then multiplied by k. And I'm going to take that R of 0, which is the initial condition right there, and I'm going to move it to the opposite side of the problem. And we're going to say plus R of 0. Okay. So now we have all our x's, everything, well, now we're going to replace the x's with the boundary conditions of t and 0. So, this means that R of t would equal t cubed divided by 3 plus t now multiplied by I. Okay? We don't have to worry about the 0 on that one because 0 cubed and 0 is 0, so we don't care about that one. And then for the next one, we also don't care about the 0. And so that's going to be plus, now, negative sine of t plus t, and that's going to be multiplied by j. Okay. Now, we do have to consider the boundaries on this one because cosine of 0 is 1. Okay? Okay. So, plus, this is going to be negative cosine of 2t divided by 4 and plus 1 divided by 4 multiplied by k. And then we have to go all the way back to the beginning of the problem and say, what was R of 0? You see R of 0 right there is j. And so that R of 0 is going to be plus j. Okay, so now we can get to our final answer of the problem. So R of t is going to equal t cubed divided by 3 plus t multiplied by I plus, this is going to be negative sine of t plus t plus 1 multiplied by j. I'm just combining that j with what's going on up there. And then plus, now negative cosine of 2t divided by 4 plus 1 divided by 4. And then that guy gets multiplied by k. Okay. And so this equation right here is going to be the position of that particle in space, beginning with the acceleration, then moving to the velocity, considering the initial velocity, and then integrating the velocity, considering the initial position, and getting our actual position function. And this is our position function in space as a function of time. Okay. And once again, this stuff becomes very important if you work at NASA. I mean, it's important for a lot of other things, but if you're trying to calculate the position of a rocket that is traveling from Earth, maybe looping around the moon or something and going to Mars, yeah, you really need to know how to do this.